Okay, so I'm going to talk about the second chapter, which is the motion in one dimension, and the first lesson that talks about the displacement and velocity. Now, the first point is about the one dimensional motion. The one dimensional motion, it means that you're moving in one direction, just like the motion of a train on a straight track. Now, we have something that is called a frame of reference. Now, the motion depends on the frame of reference. Now, this frame of reference is the system that is used to specify the precise location of the objects. A stationary observer, which is stationary by meaning that not moving, is going to have more precision than a moving observer. We have three physical dimensions of motion. The first one is displacement, which talks about the change of position in a certain direction. It's a vector quantity, which means that it has direction and magnitude, and the unit for it is meters. And to find the displacement, we should subtract the initial position from the final position. So the equation is delta x equals x, the final position, minus the initial position. Let's say, for example, you're moving from Sharjah to Dubai, and you're from Sharjah at rest, and then to Dubai at 30 kilometers. So Dubai is your final position, and Sharjah is your initial position. So 30 minus 0, which is 0 kilometers per hour, kilometers only. And if you want to go back, then it's going to be like from Dubai to Sharjah. So it's from 30 to 0, in which 0 is the final position. So 0 minus 30, which is minus 30 kilometers. The second part is the average velocity. Now, the average velocity is the total displacement divided by the total time. And the unit for it is meter per second. Now, there's a big difference between the velocity and speed. Velocity, it's a vector quantity, as I said, and it requires direction and magnitude, while speed is a scalar value or quantity, and it has no direction, so it has only magnitude. And to get the velocity, we divide the displacement over time, while for the speed, it's distance over time. And both have the same unit, which is meter per second. And the third part, which is time, it is delta t, and it's a scalar quantity, and its second, which is s. Now, having the velocity graph, first of all, we have to make sure that it's a position and time to indicate that it's a velocity graph. Now, when we have it here, it's increasing. So the position keeps on increasing as time passes. This is called positive constant velocity. But then in the second one, as the time passes, the position is becoming low, so it's decreasing. So it's a negative constant velocity. But here in the third part, or the third graph, the velocity is 0. Since the position is at rest, there is no change in the position as time passes. Now we have something called the instantaneous velocity, which is getting the specific point of a graph which is tangent. And we're going to have it as a curve. So we can have it as the slope, which is the rise over run. And now we can solve some exercises for the lesson. And in the first part, let's say if it takes you 9.9 minutes to walk with an average velocity of 1.2 meter per second to north from the bus stop to the museum entrance. What is your displacement? So now we can start with what's given. We have the time, which is 9.5 minutes, and we have the average velocity, which is 1.2 meter per second to the north. We have to make sure that we have the direction as well, and we need to find the displacement. So this part is really easy to solve. We have the given. Let's try the given to make it easier later for us. 9.5 9.5 minutes. And the average velocity, so we have delta t. We have the average velocity, which is, so V average equals to 1.2 meter per second north. And we need to find delta x. So that's what we should find, and it's in what? Meters. Now to find delta x, we have to use a specific formula. Now we know that the formula, we can use the triangle to make it easier. So we know that V average equals to delta x over delta t. Now delta x, we multiply both. So delta x equals the V average times the delta t. Now the V average, now if we notice that we have 9.5 minutes and we have the velocity here is a seconds. So the most important step is that we have to convert it. So if we're going to convert from minute to second, what should we do? We should multiply by 60. So 9.5 times 60 equals to, using the calculator of course, 570 seconds. So that's the new time that we should use. So the V average is 1.2 meter per second times 570, which equals to 684, and here's delta x. So meters, 684 meters north. We should always have the direction. That's the first part. Now the second part, it said that Heather and Matthew walked with an average velocity of 0.98 meter per second eastward. So the average velocity. And if it takes them 34 minutes to walk to the store, what is their displacement? So here again, we should do the same thing. We should always write the given to make it easier. We have the V average, which equals to 0.98 meter per second east, and it takes them delta time 34 minutes, and delta x equals to the not given, and we need to find that. So as you notice again, we have 34 minutes and here we have it as seconds. So we have to convert again. So times 60, which equals to 2040 seconds. And then here again, we can start solving it normally as using the top part, the triangle part. So I'll just do it again. The V average and the delta x and the delta t. So delta x equals the V average times delta t. V average is 0.98 times the delta t, which is 2040. And now we're going to multiply it, and we're going to have it as 1999.2, and it's going to be meters east. We shouldn't forget the direction. As long as it's given, you should always have the direction. Now we have another example. And during a race on level ground, Andrea runs with an average velocity of 6.02 meter per second east. What is the displacement after 137 seconds? So the displacement, we have to find it again. So we know that again, that we have the given part. So the V average equals to 6.02 meter per second. We have the delta t, which equals to 137 seconds, and the delta x, which equals to, not given of course, so we have to find it into meters. And again, it's the same thing, so I'll just write the formula this time. So delta x equals to the V average times the delta t. The average is, but this time as you noticed, both are in seconds. So we don't have to convert anything. So 6.02 times 137 equals to 824.74, and we're gonna try to round it, so it's going to be 825 meters east. That's for the delta x. And by this part, we're going to be like done with the first lesson. And now the second part of the lesson, which talks about acceleration. Now acceleration, it's the rate at which velocity changes over time. So the most important part here is that it's the rate of the change in the velocity. Now, as we know that we should have a formula for acceleration. So the average acceleration is equal to the delta v over the delta t. The delta v is the v final minus the v initial, and the unit is meter per second squared as well. Now acceleration, it could be a change in position, it can be a change in direction, or the change in velocity, or both. So it can change both. Now acceleration is a vector quantity, which means that it has magnitude and it has direction. Now here we have a graph, which can talk about it a little bit. Now first in A, as you can see, that it's increasing. Now something that is going to help us to know that this is acceleration, this is an acceleration graph, is if we see it here, that we have it as velocity. And here we have it as time. This is going to help a lot. Now the second part is A. It's increasing. So what does it mean? That the velocity is increasing, which is positive constant velocity. And at B, as you can see, the acceleration is 0 because the velocity is constant. We have a constant speed. It's that we don't have a change in it, but the speed is constant. We don't have a change in the velocity. And at C, it is negative since it decreases. So negative constant velocity. And here we have some relationship between the velocity and acceleration. So when the initial velocity and the acceleration, they have the same sign, then they're speeding up. When they have different signs, then it means that they're slowing down. When the initial velocity is positive or negative and the acceleration is 0, then we're going to have a constant velocity. And if we have both zeros, then it's remaining at rest. And if we have that the initial velocity is 0 and the acceleration is positive or negative, then it's speeding up from rest. So we have something called the motion of the constant velocity. It's when the rate of the acceleration is constant. So we have some equations that we can control the motion with. These equations are called the kinematic equations. So the first one is delta x equals half vi plus vf times delta t, and we use it when there is no acceleration. As you can see that we don't have an acceleration here. The second part is vf equals vi plus a delta t, and here what's not given, the displacement, which is delta x, isn't given. And then the third one, which is delta x equals vi delta t plus half a and delta t squared, and here the vf is not given. And the last one but not least is the vf squared equals to the vi squared plus 2a delta x, and here we don't have delta t, so this is going to help us. So anytime we have something from these missing, then we're going to know which equation to use. And to revise the units, the initial velocity and the final velocity, they have the same unit, which is meter per second, and the delta time, the delta t is seconds, which is s, and a is meter per second squared. Now let's solve some exercises as well for this part. Okay, so in the first part, with an average acceleration of 1.2 meter per second squared, how long will it take a cyclist to bring a bicycle with an initial speed of 6.5 meters squared, 6.5 meter to a complete stop? Now this part is really easy. So we have the average acceleration given, which is negative 1.2 meter per second squared. And we have the initial speed and the final speed. And when they say a complete stop, they mean it as it's into zero. And then we start writing the given to make it easier. So we have given as A, which is negative 1.2 meter per second squared, and the VI equals to 6.5 meter per second, and the VF equals to 0 meter per second, and we have to find the delta T. So we know that A equals to delta V over delta T. Now to get delta T, we can use the triangle here again. So A, delta V, and delta T. So we can say that delta T equals to delta V over A. And we start replacing. So minus 6.5 over minus 1.2, which equals to 5.416. And here, to make it easier, the delta V, if you get confused, it's the VF minus the VI. So it's 0 minus 6.5, which is negative 6.5. So the delta T is around 5.4 seconds. And now, the second part of another question is, suppose a treadmill has an average acceleration of 4.7 times 10 to the negative 3 meter per second squared. Part A of the question says, how much does its speed change after 5.0 minutes, which is 5.5? And let's start solving the A first, part A. So we have given that A equals to 4.7 times 10 to the negative 3. And we have the time. And we have delta T equals to 5 minutes. You have to make sure we have here seconds, here minutes. So we have to convert. By converting, we mean that we're going to multiply it by 60 to get the right one for it. Times 60. Which equals to 300. And we have to find the speed, which is delta V. So it's missing. Now to have it, we can use the acceleration formula, which equals to delta V over delta T. We can use again here the triangle to make it easier. So you know that you have here A, which is delta V, and delta T. Now delta V, so delta V equals to A times delta T, which equals to 4.7 times 10 to the negative 3 times 300. So it will equal to 4.7 times 300, which is 1410 times 10 to the negative 3. We have to move the points. It's going to equal to 1.4 meter per second. So that's for the delta V. That's part A. Now we're going to solve part B, in which they said if the initial speed is 1.7, what is the final speed? This is easy. Now we know that if we subtract the initial from the final, we want to have delta V. So what you can say is that, so the Vf minus the Vi equals to the delta V. We know this from already. So we can say that Vf is the one that you want to find, minus the Vi, which is already given, which is 1.7, and the delta V, which is 1.4. So we take this to the other side and we'll add it. So Vf equals 3.1 meter per second. And the last one, which is the last example in this lesson, we have a car with an initial speed of 6.5 meter per second, accelerates at a uniform rate of 0.92 meter per second squared for 3.6 seconds. Find the initial speed and the displacement of the car during this time. Now the first thing that we know that we're going to use from the kinematic equation is uniform. Anytime we see uniform or constant accelerating uniformly, anything uniform or constant, then we have to use one of the kinematic equations. And we have them here to help us decide which one we're going to choose. Okay. So what's given first? To make it easier as always, we start with what's given. We have Vi equals to 6.5 meter per second. We have A, which equals 0.92 meter per second squared. And we have the delta T, which equals to 3.6 seconds. First, they're asking for the final speed, and then for the displacement. So here they want two stuff from us. So first we need to find the Vf, and then we need to find the delta x. Okay, so here, if we want to find for the Vf, now which equation has the Vi and A and delta T? The second one. As you can see, everything is given. Vi, the A, the delta T, and the Vf is the one we're going to find. So what we just do is we replace. So we write the rule here again. So Vf equals Vi plus A delta T. And here's easily we just start replacing it. So 6.5 plus A, which is 0.92, and delta C, which is 3.6. We multiply, we're going to get 3.312 plus 6.5, which equals to 9.812. So it's around 9.8 meter per second for the Vf. We're done with the first part of the question. Now the second part for the delta x, what we can do is, so delta x, we need an equation also again that has the Vf, the delta T, the Vi. You can use any equation that has one of these, but the easiest one would be the first one. So here we're going to use the first one in this part. So we know that delta x equals to half Vi plus Vf delta T. So half 9.8 plus 6.5, which is 3 times 3.6. So half, and we have it here as 16.3 times 3.6. And when we divide by 2, we're going to get 8, and so this is 16.3. And you can even use the calculator to make it easier for us if you have like some complications. So if we get 16.3, if we want to divide it by 2, we're going to have 8.15. We're going to have it as 8.15 times 3.6, which equals to 29.34, which is around 29 meters, which is delta x. So by that will be the lesson, as I just like summarized and explained the equations and the kinematic equations, and we use them when they inform us that it's uniform or constant. So anytime you have these, we use the kinematic equations. Thank you.